Hello. So I wanted to talk for a moment about calculators, specifically graphing calculators. And you have access to graphing calculators even well beyond what I had when I was in school. Not only do you have physical graphing calculators, which I had, but you can also just go online on your phone and you have access to calculators through that. There's various web pages, including Desmos, which is really nice, that will do calculations for you, will do graphing calculations for you. Um, this is a very nice piece of software, but it's not perfect, and no graphing calculator is going to be perfect. No calculator is perfect. Every single one has its own flaws, and you could manually go into the code of the calculator and fix up those flaws, but there'd still be other flaws left over. This is, in fact, a thing that mathematicians have proved, that you can't have a perfect calculator. Um, uh, so it's important to be able to anticipate what should this graph look like? And so if the graphing calculator gives you something that's very different from what you think the graph should look like, it's important to have an intuition for what the answer should be on your own, so that you can say, no, the graphing calculator is wrong in this case. Um, and that's true also if you're just doing calculations, not just if you're doing graphs, but also if you're doing calculations. And I'll show you some examples of those as well. So it's really important to know the mathematics of how to be able to figure out what a graph looks like, how to do some algebra to simplify some calculations. All of that stuff is super important to be able to check the work of your calculator, because no calculator is perfect. Let me show you my favorite way that a graphing calculator can get confused, and that's if we ask it, what is -2 to the power of x? And I warned you in class when we were talking about exponents, exponential functions, that, -2 should not be the base of any exponent. You can make sense of some things, like -2 to the power of 3 is -2 times -2 times -2, which gives you -8. Okay, so you can make sense of that, and -2 to the power of 2 is -2 times 2, which is +4. As we can see, these things alternate between being positive and negative. Um, and what Desmos has done is it's tried to kind of fill in the pattern by plugging in some other points and trying to figure out what the result is when it does that. The result that you get looks something like this. Desmos tried plugging in 1.2, and it decided that -2 to the power of 1.2. 1.2, remember, is like 6/5. And so when it did -2 to the power of 6/5, it got 2.297. Let's see what this point, can we figure out what this point is down here? Well, it's telling us that -2 to the power of 2 is 4, so that's something. Uh, yeah, it gets very confused. And that's fair. It really doesn't make sense to have -2 to the power of most fractions, right? Because something even as simple as -2 to the power of 1/2, that's going to be the square root of -2, that isn't going to exist. But the thing that I really like about this example is that as we adjust the width of the viewing window, and you can do this also by changing the width of your browser window when you're looking at this interactive. The graph changes. So here we see just a scattering of points. So here, can we even figure out where these points are? Oh, that's weird. It's uh, it thinks that -2 to the power of 0.2, which is 1/5, is negative 1.149, but it didn't draw a dot there. This is very strange. And as we adjust the width of the browser window, we can see the graph almost completely disappearing. We can see some flickering. We can see, again, this sort of two curves that show up. Let's see if I can get, there's like a few more things. Yeah, here we go. There's this one, which is just the bottom half of the graph. We get different graphs depending on the width of the browser window, depending on the width of the graph window. And that's kind of, it's not ideal. Um, uh, so in truth, the real matter is that you shouldn't be doing -2 to the power of anything fractional, right? -2 to the power of 3, that's fine. -2 to the power of any integer, that's perfectly fine. But -2 to the fractional power, you want to be really careful with that. And so that's why it's having trouble with all of these decimals and stuff. And Desmos does not get exponents perfectly. Let's say we wanted to do 10 to the power of -100. Well, it knows what that is, right? This is just 0.0 and then 99 zeros and a 1. And it's very important to remember that 10 to the power of -100 is very, very close to 0, but it's not equal to 0. It's just the tiniest bit larger than 0. But if we do 10 to the power of -1000, Desmos says, oh, that's 0. But it isn't 0. It's just a tiny bit larger than 0, right? It's 1 followed by 999 zeros followed by 1. And you say, oh, well, that's a rounding error. That's not that big a deal. Well, what happens if we wanted to multiply this by 10 to the 1000th? Now we know the rule. We know the rule for exponents. We know exactly what 10 to the -1000 times 10 to the 1000 should be. All right, we add those exponents together. -1000 plus 1000 is 0, so we're looking at 10 to the power of 0. So we're looking at 1 here. Desmos does not say that. It says the answer is undefined. Whereas, we who know a little bit of algebra know that this answer here should be equal to 1. Let me show you a few other cases where graphing fails. So here we have a function here, and it's actually not that hard to figure out. If we had a few more weeks, I would talk about how we could figure out what the graph of this function looks like. Specifically, it looks like this nice, so here we see the graph, this actually is the graph of 1 over x. It's been shifted over 1 unit to the left. And there's actually a hole in the graph here. Desmos doesn't draw the hole, but there is a hole here at, oh, there we go. I've gotten Desmos to draw the hole. At -2, if you try plugging -2 into the function here, you'll get 0 over 0, which is, of course, undefined. Right? You can't do 0 divided by 0. And so there's actually a hole here at -2. And so this is what the graph should look like. But let's actually take a look at what the graph really looks like when we zoom in on this point here. We have to zoom in very, very closely. But as we can see, things are already starting to go a little bit awry. And as we get closer and closer, something really strange is happening here. This is definitely not what we expected to find when we zoomed in on this point here. When we zoom in on this point, the graph should look like, let's turn off this point here. It should look like this, right? The graph should be almost a perfectly straight line, because when you zoom in on graphs, they tend to wind up looking like perfectly straight lines. That's what calculus is all about, actually. It should look like a perfectly straight line with a hole in it. Right? And we draw, again, if there's a point that's missing from a graph or from an interval on the number line, we draw that as a big old filled in or empty circle to indicate that that point isn't there on the graph. And so this is what the graph should look like. But again, when we zoomed in really, really close, we got this really weird behavior. And that's not what the graph looks like. This is due to rounding error inside the calculator. You could teach a whole class as to like what's going on behind the scenes of the calculator that causes it to have this really kind of interesting behavior when it goes to graph these things. Why do we get these kind of diamond shapes showing up? And why do they not look quite as nice when we're over here? There's lots of interesting questions that you can ask about why is Desmos giving us this graph in particular, which again, I'll remind you, is wrong. This graph at this zoomed scale should look like an almost perfectly straight line with a little hole in it. This is not what the graph actually looks like. This is an error due to the graphing calculator. And I also want to show you, there's this website called wolframalpha where you can access Mathematica through the internet. One of the graphs that you can ask it to figure out what the graph looks like is this particular function here. We haven't done nearly enough in this class to know what this graph looks like here. Nonetheless, it's pretty clear that the graph should not look like this. It's all jaggedy and lots of noise. In fact, the graph should look like a nice smooth curve, again with a hole in it somewhere at x is equal to 0, because if we try plugging x is equal to 0 into this function here, we're going to get 0 over 0, which is undefined. So there should be a hole at x is equal to 0, and it should be this nice smooth curve with a hole in it. So again, we see a lot of cases where our calculators don't give us quite the right answer, and this is inevitable. No calculator is perfect. No calculator can be perfect. This is a mathematical fact. Every calculator is going to have some flaws in it. Now, is it possible that somebody behind the scenes on Desmos might say, "Oh, hold on, like we know what 10 to the minus 1,000 times 10 to the 1,000th is. Let's fix that." Sure, the people behind the scenes at Desmos could introduce a more robust calculator, maybe that does a little bit of algebraic simplification to try to solve these sorts of problems algebraically without having to try to calculate. The issue here is that it's trying to calculate 10 to the minus 1,000 and 10 to the 1,000th and then multiply those numbers together, and 10 to the 1,000th is just too big for it, right? We actually saw 10 to the 1,000th alone is too big for the calculator, even though we know exactly what this is, right? It's 1 followed by 1,000 zeros. It's going to take a little while to write down, but like what's stopping us? Um, so it's important to remember, graphing calculators aren't perfect. Ordinary calculators aren't perfect. Even these online calculators aren't perfect, even though they have these massive calculator servers that are doing these calculations for you. None of them are perfect, and so that's why it's important to know enough algebra to be able to anticipate what these graphs look like.